Okay, so in the last video, we left off by talking about the concept of a potential divider or a voltage divider. And so just to recap, a potential divider or a voltage divider, they're both the same thing, is basically a type of circuit that you create by having two or more series resistors. And the idea is that you have some input voltage, what we call Vin, that you want to split or you want to divide to a smaller voltage. So for example, let's say you had a 6-volt battery and then you had a light bulb that only works correctly if you have 3 volts. Well, you can't just like take a 6-volt battery and cut it in half. That doesn't work. And so by using the potential divider circuit, we can take a 6-volt battery and extract only 3 volts from it to output to our light bulb. And so in this example then, we would put the light bulb here in the circuit where we call V out. Okay, now Vin is what we call the input voltage. That's just the EMF from the battery or from the cell. The output voltage is usually across R1 or R2. It doesn't matter, but it is parallel with either R1 or R2, meaning it has the same voltage as one of those two resistors. And in the last video, I derived for you the the voltage divider equation. And you do need to be able to do that derivation because this equation is not given to you. So I would suggest you go back and take a look at that. But basically, the output voltage is given by Vn times, and I think in the derivation, I assume that the output V out is across R2. And so that is Vn times R2 divided by R1 plus R2. Again, if you want to see where that equation comes from, please go watch the end of the last video um, so you understand how that derivation works. And so that's kind of where we left off in the last video. Okay, so in this video, the last thing we're going to learn about in this unit is how to do different types of problems with voltage divider circuits. Okay, so let's take a look. Okay, so the first example we're given is to find the output voltage if the battery has an EMF of 9 volts. R1 is a 2200 ohm resistor, and R2 is a 330 ohm resistor. Okay, so we're asked to find V out. Now, it really helps here if you just happen to remember the voltage divider equation. But let's just say you don't, and let's say you have to go from scratch. Okay, how would you go about finding V out? Well, V out is parallel with R2, and so V out would be equal to I times R2, because if these two are parallel, they have the same voltage by definition, and the voltage across a resistor is just given by V equals I times R. Okay, now, because R1 and R2 are in series, that means the equivalent resistance for the entire circuit is R1 plus R2. Okay, and so if I want to find I can find the equivalent resistance, use V equals IR to find the total current I, and then I can plug in, I can solve this equation for I and substitute into my original equation. That's basically how the derivation went in the last video. Okay, so if you don't happen to remember the voltage equation, you can derive it. Okay, and so if you make that substitution, then you get V out equals Vn times R2. Here it's R2, by the way, because the V out is in parallel across R2. Okay, now if V out was across R1, then it would be Vn times R1 divided by R1 plus R2. That's why understanding the concepts behind the derivation is important. Now, once you get to the voltage divider equation, it's just a matter of plugging in and solving. Okay, so the EMF of the battery, that's Vn, that's going to be 9 volts. Okay, R2 is given as 330. And then we divide by R1 plus R2, so 2200 plus 330. And I'm just going to type that into my calculator really quickly, and then I will have the answer. Okay, so 9 times 330 divided by 2200 plus 330. Okay, so that is going to be about 1.17 volts. And so that is going to be V out. Okay, pause it there if you need to look at that some more. Okay, so that was just a really kind of basic voltage divider equation problem. Okay, here you see um, the solution to that. Now, let's step it up a notch. Here we're given basically the same setup, but we're asked to find the value of R2 if the battery has an EMF of 9 volts, R1 is a 2200 ohm resistor, and we want an output voltage of 6 volts. And again, why would we need to do this? Well, let's say we have a device that requires 6 volts, okay, but we only have 9 volts to give. We need a way to divide that. All right, so if you happen to remember the voltage divider equation, that's helpful. Otherwise, you have to derive it like we did in the last slide, but that's going to be V out equals Vn times R2 divided by R1 plus R2. Okay, now here we're given V out as 6 volts, Vn is 9 volts. We don't know what R2 is, we're asked to find that, and so that's going to be 9 times R2 divided by 2200 plus R2. So I'm going to have to do a little bit of rearranging here. I'm going to have to multiply both sides by 2200 plus R2. So that gives me 6 times 2200 plus R2 equals 9R2. I need to distribute that 6. Okay, so I'm going to do 6 times 2200. That's 13,200 plus 6R2 equals 9R2. And then subtract both sides and divide. Okay, so just kind of basic algebra at this point. That's 3R2. So R2 needs to be, let's see, what is that? 4,400 ohms. Okay, so slight step up in difficulty there, but not anything too crazy. Okay, so pause it there if you need to look at that some more. Okay, and there you just see the solution for that question. Okay, so now we're going to step it up a notch. Where you see voltage divider circuits a lot is in what I like to call sensor circuits. And when I say a sensor circuit, I mean a circuit that is able to detect some type of change in the environment and use that to change the output voltage for some reason. So here is an example. We have a voltage divider circuit. But now if you look at the symbol, R1 is a normal resistor, but R2, that is the symbol for an LDR. Now, if you don't remember the symbol for an LDR, I do want to remind you, all the circuit diagram symbols are in the IB physics data booklet, so you don't have to have them memorized, but that is an LDR. Okay, the R2, the one with the arrows pointing towards it. Okay, so it says a light-dependent resistor, an LDR, has R equals 25 ohms in bright light and R equals 22,000 ohms in low light. So remember that an LDR works by when you increase the light intensity, the resistance of the LDR decreases. Okay, now if you look at where we would put V out is placed in parallel across the LDR, and it's an electronic switch. And it says an electronic switch will turn on a light when the potential difference is above 7 volts. What should the value of R1 be? Okay, so basically what we have is we have a setup where, well, if it's dark, we want to turn on the light. Okay, and so you might have seen these before, like maybe like a really basic night light or some different types of rooms have these where you open the door and when it detects the ambient light, it knows to turn the lights on automatically. Okay, and so that type of circuit. Okay, so how do we go about approaching this? Well, it says that we want the switch to turn on a light when the potential difference is above 7 volts. Now we have to use a little common sense here because it looks like there's two different resistances given, but they're both for the LDR, and we're asked for the value of R1. Okay, so we have to use a little bit of common sense. Now we know Vn is 9 volts from the picture. Okay, so I know what Vn is. V out, in order for the switch to turn on, I need V out to be equal to or greater than 7 volts. Okay, now how do I know which of these two resistances to use? Well, let's think about that. If I want the light to turn on, do you think that's going to happen when it's already bright or when it's dark? Well, probably when it's dark. Okay, so you could also have this type of circuit, by the way, for like street lights. A lot of street lights operate on a typer, or they can be operated remotely, but some of them have LDR circuits built in so that when it's nighttime, the lights automatically turn on to light up the roads. Okay, so we're going to use the resistance of the 22,000 ohm resistance um, as our R2 value because that's the situation in which the voltage would go above 7 volts. So when I go to plug in, I have my voltage divider equation. When this happens, R2 is going to be 22,000. So V out, I need to be 7. V in is going to be 9. R2 is going to be 22,000 ohms. And so here it is just a matter of doing a little bit of algebra and rearranging to get R1 by itself. Okay, now I trust your algebra skills, and so I'm not going to go through all of that. But it would be 9 times 22,000, and then you would subtract from both sides 7 times 22,000, and then divide by 7. So you should get a value that is approximately equal to 62,086 ohms, and that would be the answer to the question. Okay, so this one requires a little bit more thought because you have to understand, like, in what situation do you need the light to turn on? Okay, so if you want to build this type of circuit, then you would just go to your box and pick out a resistor R1 that is somewhere around 6200 or 6300 ohms. Okay, so there is the given solution. Now, I want you to try this next one on your own. Okay, this next one involves a thermistor. And this first question is another kind of concept question that really is a little tricky. And so I'm going to explain the concept for A, and then I want you to try to do the calculation for B on your own. So here we have a thermistor. So R1 here is a thermistor. That is the symbol for a thermistor. If you didn't know what that was, you would look it up in the IB data booklet. Okay, so R1 is a thermistor, and V out is going to be across R2 in this case. So it says a thermistor has a resistance of 250 ohms when it is in the heat of a fire, and a resistance of 65,000 ohms when at room temperature. An electronic switch will turn on a sprinkler system when its potential difference is above 7 volts. So think about what this means. This is basically where if you have like a sprinkler system in like a room or something, this is how it would know to set off the water to put out the fire. Okay, so the thermistor detects the change in temperature, and that changes something in the circuit that activates the switch, and then the sprinkler system goes off to put out the fire. Okay, so this is a really like real life kind of applicable problem. All right, so first question says, should the thermistor be R1 or R2? So there's a couple concept things going on here. Number one, when there is a fire, we want um, we want the voltage to go up across R2. How do I know we want the voltage to go up across 2? Well, because it says in the problem that the switch is going to like turn on the sprinkler system when the voltage goes above 7 volts. That means under normal circumstances, we want the voltage, we want V out to be less than 7 volts. Okay, we don't want the sprinkler system to go off under normal circumstances. We want a setup so that when the temperature goes up, that voltage also goes up, the V out goes up. Okay, so here's something you need to know about voltage dividers. Okay, this is a pretty key concept. Okay, so listen carefully. Because R1 and R2 are in series, they have the same current going through them. Okay, between R1 and R2, those two voltages have to add to be 9. Okay, that's just kind of common sense. Listen carefully. If the resistance of one of the components decreases, the voltage there is also going to decrease. Okay, if the resistance of one of the two components decreases, the voltage is also going to decrease. The reason is just from V equals I times R, these two components have to have the same I. Okay, so if the resistance R1 goes down, that means the voltage there also goes down. Okay, so how does that affect R2? Well, remember the voltage across R1 and the voltage across R2 have to add to 9 volts. That means if the voltage across R1 goes down, the voltage across R2 would have to go up to compensate because again, they have to add to be 9 volts. Okay, so let's put all this together. If there's a fire, we want the voltage across R2 to go up. Okay, that is basically the same thing as saying we need the voltage across R1 to go down. That way the voltage across R2 will increase. What situation would make the voltage across R1 go down? Well, that would be if the temperature increased, like if there was a fire. Okay. Okay, so if the thermistor was at R1, just like how it's currently drawn, if there is a fire, R1 is going to go down. That means the voltage across R1 is going to go down. That means the voltage across R2 is going to go up, increase above 7 volts, and set off the sprinkler. In other words, the way it's drawn now is the way it's supposed to be drawn. Okay, so when the question says, should the thermistor be R1 or R2, it should be R1. Okay, so the way it's drawn now is how it should be. If you were to switch the thermistor and put it like at the bottom, so that so that V out was across R1, then the circuit would be backwards and it wouldn't work correctly. Okay, basically what would happen in that situation is the sprinklers would always be on and then they would turn off when there was a fire, okay, which would be bad. Okay, so keep that concept in mind. The two voltages have to add to be V in, so if one voltage goes down, the other goes up. Okay, if the resistance goes up, the voltage also goes up, okay, because V equals I times R. Okay, so try to do this calculation on your own. Okay, now we're asked what should R2 be in order for the circuit to work the way it's supposed to. Okay, so try to do this calculation on your own. Okay, so we want V out to be at least 7 volts. Okay, so we have our voltage equation and we want V out to be 7 volts, or our voltage divider equation. V in is 9 volts. Okay, notice that R2 is our V out, and so I multiply by R2, and then I divide by R1 plus R2. But which of the two resistances do I use? Well, we only want this to happen if there is a fire. Okay, which means we need to use the resistance that would be there if there was a fire. All right, so that would be 250 ohms plus R2, and now it just comes to doing some algebra. Okay, multiply that by both sides, like this. That's equal to 9 times R2. I distribute out, and I'm just going to write down the answer just to save on time. Okay, but it's not that difficult algebra to do. Okay, so you should get R2 equals 875 ohms. Pause there if you need to look at some. Alrighty. Okay, so I want to take a look at one more question. This is a concept question, and this one is actually on the worksheet, and so you might have already seen the answer to this question. Okay, but just to make sure you really understand the concepts of what we've been talking about with the potential divider. Okay, so 38, this is a multiple choice question. 38 says a light-dependent resistor and a fixed resistor are connected in the potential divider circuit shown below. The voltmeter reads 3 volts. which of the following changes would cause the reading on the voltmeter to increase? Okay, so I'm going to make this a little bit bigger so you can fully see. Try to answer this question on your own. Which of the following changes would cause the reading on the voltmeter to increase? Okay, so let's use some logic here. If we want the voltmeter reading to increase, that is the same as saying that we want the LDR to have a bigger voltage. We want the voltage on the LDR to increase. Why? Well, because the voltmeter is in parallel with the LDR, and so they have the same voltage by definition. Okay, so in other words, going backwards, we now want a situation where the voltage on the LDR will go up. Now, I said before, if the resistance goes up, the voltage will also go up because these two components have the same current. Okay, the only thing separating them is their resistance. All right, so for the LDR, in order for the voltage to go up, we need the resistance of the LDR to also increase. Okay, now how do you do that? Well, shining a light on an LDR is going to decrease the resistance. Okay, so the opposite of that would be decreasing the amount of light shining on the LDR, and the answer would be D. Now let's take a look at why the other ones would not work. All right, what would happen if we swap the positions of the LDR and the fixed resistor? Okay, so let's think about this. Vn is 5 volts. The voltmeter currently reads 3 volts. That means as we speak, we have 2 volts here, and we have 3 volts here. If I switch those two components, the voltmeter would then read 2 volts. Okay, well, that would not be an increase, that would be a decrease. So A is out. B says increasing the resistance of the fixed resistor. Okay, but I said before, more resistance means more voltage. Okay, in other words, if I increase the resistance here, I increase the voltage here. But I only have I only have 5 volts to work with. So if the voltage here goes up, the voltage here has to go down because those two voltages still have to add to be 5. Again, that's going to cause the reading on the voltmeter to decrease, not increase. And so B is also out. And C is out because if you shine more light on the LDR, the resistance is going to go down, which means the voltage is also going to go down across the voltmeter. Okay, and so hopefully you got answer choice D, or if not, you at least understand better the concept of why the answer is D. Okay, now for the most part, we're basically done. This is the last video going over notes. There are more circuit divider questions here in this worksheet, but I believe I already posted a video with the solutions going over everything on this worksheet. Now, of course, I would recommend that you do those problems before you come to next class, because if you have any questions, I want to be able to answer those. I also highly recommend that you try to do all these questions on your own before you look at the solution video. Okay, because the only way you're really going to understand and make meaning of what you're learning is if you try and struggle with the problems yourself, and then you can go back and look at the solutions and make the connections of, oh, I did that correct, or oh, I did that incorrect. Okay, so try to do all of these problems first on your own before you look at those solutions. Okay, so this next test is going to cover topics 5.2 and 5.3, and a little bit at the end of 5.1 having to do with drift velocity. All right, so please come to class prepared to ask any questions you have about this unit. And then the class after that, we will be taking our test over circuits. As always, please let me know if you have any questions, and I'll see you guys in the next video.